Hello everyone. In this part of the video, we will talk about quadratic forms. As compared to the previous part, there will be a much less focus on the practical applications of quadratic forms, since it is much a theoretical concept, and we will mainly focus on what exactly quadratic forms are useful for and what they represent. So, yes, what exactly is a quadratic form? A quadratic form refers to a polynomial in multiple variables which is composed of all terms of degree 2. In essence, it is a homogeneous polynomial, which are a set of polynomials whose terms have all whose terms all have the same degree, of degree 2. It is a homogeneous polynomial of degree 2. Effectively, any vector valued scalar function is a quadratic form if it can be expressed as follows, where f of x is equal to the summation of I from 1 to n and j from 1 to n of aij xi xj, where x is equal to x1 to xn for some aij belonging to the real numbers for all I comma j, and f is a thus effectively f becomes a mapping from Rn, i.e. the vector space of x, to the real numbers R. It is to be noted that in general we can extend the notion of quadratic forms to the complex case. However, since we are discussing practical linear algebra, we will not do so, since that is of much less use in most practical scenarios, and only holds for many theoretical cases only. So effectively, from the notion of a quadratic form, one can define a quadratic space. A quadratic space, which, as per the name, is a vector space which is associated with a quadratic form, effectively similar to the inner product space, which is a vector space associated with the notion of an inner product. A quadratic space is a vector space with an associated quadratic form, which is essentially just a mapping from that from a from for all the vectors in Rn to the real number 9. Using linear algebra, one can easily express this in terms of vector as f of x is equal to x transpose ax, where the elements of n cross n are of the form aij, where aij can be seen from the above summation. An important property of the quadratic form is that f of lambda x is equal to lambda square f of x. Thus, it is not exactly an eigenfunction. It is not exactly a linear transformation, but rather a quadratic transformation, since multiplying the input by pre-multiplying the input by a scalar lambda squares the value of the output. As mentioned previously, we have restricted the scope of this discussion to the field of real numbers R. Further, it is to be noted that the quadratic form of a matrix of a functional mapping from Rn to R is not unique, considering that for the coefficient of xij, where I is not equal to j, there can be multiple combinations satisfying aij plus aji is equal to the coefficient of xij. Say my quadratic form is in R2, and it is of the form ax square plus bxy plus cy square. Here, we can express the bxy term as b by 2 plus b by 2 in the matrix, or we can represent it as b plus 0 or 0 plus b, or many other such combinations. Specifically, however, if we choose aij is equal to aji is equal to the half of the coefficient of xij, we will get a quadratic form matrix A, which is actually symmetric. This symmetric form of the quadratic form matrix has much more relevance in many practical applications, and it is the conventional quadratic form which we use when we come to the next part of this discussion. It is to be noted here that when we refer to the quadratic form, it is generally considered that the quadratic form can refer to the quadratic form matrix as well. They can be used as interchangeable terms. Similarly, if we choose aij is equal to 0 when I is greater than j, or when I is less than j, we get an upper and lower triangular form of A respectively. Now, the quadratic form and its relation to the spectral theorem. As is known that the quadratic form of a function can be chosen so as to make it symmetric, as mentioned here. So if we take that symmetric quadratic form matrix where A is equal to A transpose, and f of x is equal to x transpose ax is the quadratic form for n cross n and x belongs to Rn, we can apply the spectral theorem. Now, the spectral theorem, note that here I accidentally use the word spectral decomposition theorem. Instead, spectral theorem and spectral decomposition are separate things. However, as a consequence of the spectral theorem, which states that every Hermitian matrix has an orthonormal eigenbasis, which means that the eigenvalues and eigenvectors of an Hermitian, or in general Hermitian, or specifically a symmetric matrix, can be made into an orthonormal basis, which also relates to the discussion previously in the case of Gram-Schmidt orthogonalization procedure. The spectral decomposition, the spectral theorem says that such a decomposition is possible, and we can use the spectral decomposition on A, which we have established is symmetric, to get a form of A is equal to V transpose dV, where V is an orthogonal matrix of vectors of eigenvectors associated with A, and D is the diagonal matrix of eigenvalues, where lambda I and Di, as noted here, where lambda I and Di form an eigenvalue eigenvector pair for the matrix A. Using the spectral theorem to decompose A to V transpose dV, we can find the quadratic form in its canonical form, which is another way of expressing the same quadratic form, as f of x is equal to x transpose ax, substitute A is equal to V transpose dV, and we get that f of x is equal to Vx transpose D into Vx. This implies that we can, through an orthogonal change in the variables, diagonalize the quadratic form if we take the orthogonal transformation x tilde or x bar is equal to Vx. Here Vx represents an orthogonal transformation on A, since V is chosen to be an orthogonal matrix, and we know that it must exist since by the spectral theorem. Thus, the quadratic form f of x is equal to the quadratic f of x is equal to x transpose ax is equivalent to the quadratic form of another vector for another matrix D applied on x bar, where x bar is the transformation Vx, and it is equivalent to x bar transpose dx bar in this case. It is to be noted that essentially this does not mean that these two transformations are equal within the same vector space, but essentially if we change the mapping of x to Vx, we can get the same associated quadratic forms. It represents a transformation from the normal form of the quadratic form to its canonical form in terms of diagonal vectors. Essentially, when we do this, we can express it as lambda x1 bar square plus lambda 1 x1 bar square, lambda 2 x2 bar square plus so on, lambda 3 x3 bar square, and so on and so forth till we get to lambda n xn bar whole square. Now, this diagonalization has several far-reaching consequences which relate to optimization or probability, etc. We can just summarize this as follows. On obtaining the canonical form of the quadratic form, or essentially on obtaining the eigenvalues of the symmetric matrix A, we can comment on its definiteness of the matrix. The definiteness of the matrix is a property which which is associated with symmetric or Hermitian matrices, and it states that if the eigenvalues of a matrix are greater than 0, the matrix is positive definite. This implies that for any non-zero vector x, f of x is equal to x transpose ax will always be greater than 0 irrespective of the choice of vectors. This can be seen on applying the canonical form. We have lambda 1 x1 bar whole square plus lambda 2 x2 bar whole square, so on and so forth. And since lambda 1, lambda 2 are all greater than 0, and since x is not equal to 0, even x bar whole square cannot be equal to 0. From here, we can say that x transpose ax must be greater than 0. If instead all the eigenvalues are non-negative, i.e. they can be 0, but they can also be greater than 0, the matrix is termed as positive semi-definite. In this case, x transpose ax is greater than equal to 0 for all x not equal to 0. Here you can see that all positive definite matrices are also positive semi-definite. However, sometimes authors prefer to use positive definite to refer to only those matrices which are positive semi-definite, to only refer to those matrices which are not positive definite but positive semi-definite alone. Similarly, analogous to the positive definite and positive semi-definite case, where we look at the positive sign of the eigenvalues, positive or zero sign of the negative values. So we can, if we take the negative sign of the eigenvalues, we have a negative definite when all the eigenvalues are less than zero. In this case, x transpose Ax is less than zero for all non-zero x, and negative semi-definite, where all the eigenvalues are non-positive, and x transpose Ax is less than equal to zero for all x not equal to zero. Similar to the positive definite and positive semi-definite case, and all negative definites are by definition negative semi-definite. It is interesting to note that a quadratic form for which f of x is equal to 0 implies that x is equal to 0 is the only possible solution. This means that x is equal to 0 is the only solution to the quadratic form equation of x transpose Ax. This is termed as an anisotropic quadratic form. And such quadratic forms must be definite in nature, i.e. they must either have positive definite or negative definite eigenvalues. All other quadratic forms are termed as isotropic in nature, since they can have multiple solutions to the equation f of x is equal to 0. Now, another theoretical concept which we associate with the quadratic form is that we associate a bilinear form with every quadratic form. Now, the bilinear form is equivalent, is essentially the quadratic form for two separate inputs, and we define it as phi, and say we define it as phi of xy, then we say that phi of xy is equal to half of f of x plus y minus f of x plus f of y, where phi is a mapping from the Cartesian product of Rn with itself to the real number space R. Essentially, if f of x is equal to x transpose Ax, then phi of x y is equal to phi of yx is equal to y transpose Ax is equal to x transpose Ay, and we can express the same thing in terms of summation of Aij xi xj and Aij xi yj and Aij yi xj. Further, it can be noted that when we take x is equal to y, we get the original quadratic form, and that phi of x comma x is equal to f of x. Thus, we have already noted that the bilinear form is symmetric, and this allows us to extend the notion of orthogonality beyond the dot product, which is the associated functional mapping in an inner product space. Essentially, if we take phi of xy is equal to 0, we can define them as orthogonal for that quadratic space, i.e. the space where we associated that specific quadratic form, we can define orthogonality when phi of x comma y is equal to 0. In general, one can define an inner product space as the association. In general, we can see that the inner product space is a specialized case of the quadratic space, i.e. one where the associated quadratic form is the identity matrix, and similarly, its bilinear form represents the dot product or inner product function. This is interesting to note, since all of these properties, since the way we define the bilinear form as f of x plus y minus f of x, to be noted here that it's supposed to be minus f of x minus f of y instead of minus f of x plus f of y. However, we can take f of x plus y minus f of x minus f of y as similar to the notion of A transpose B is equal to A plus B transpose into A plus B minus A transpose A minus B transpose B upon 2, which is the similar definition of an inner product in terms of the L2 norms, or in terms of the self norm of in terms of the L2 norm of a vector for an inner product space. Now, as mentioned previously, the definiteness of the symmetric quadratic form matrix and its diagonalization has important consequences in optimization theory, since often we consider symmetric forms which have a positive definite or negative definite, which have some sort of definiteness associated with them, to be much more useful as compared to those which are indefinite. Further, quadratic forms and quadratic spaces are useful in geometry, particularly in the study of conic sections and their analogs in higher dimensions, such as hyperboloids or hyperparaboloids, which are often defined as the sum of a quadratic form with a linear equation of the form the surface of x can be defined as x transpose Ax plus B transpose x plus C is equal to 0. One of the major applications where quadratic forms are seen, which often people do not associate with the quadratic form, is the multivariate normal distribution. The multivariate normal distribution, also known as the multivariate Gaussian distribution, has the specific form of f of x is equal to as defined here. And here we can see that sigma acts as a symmetric quadratic form matrix for the mean centralized x minus mu vector. And satisfying for it to satisfy all the properties of probability, we note that it must be positive definite generally and positive semi-definite. However, if we get a sigma such that a capital sigma such that it is only positive semi-definite but not positive definite, i.e., it has a zero eigenvalue, that implies a degeneracy within the quadratic form matrix. The multivariate normal distribution also finds many applications in machine learning, since the multivariate normal distribution is one of the most fundamental distributions in probability, which is applied in many linear in many machine learning algorithms such as linear regression or randomized smoothing, amongst others. They also have, it also finds the concept of quadratic spaces and quadratic forms, and the bilinear form has usage in number theory, geometry, topology, and probability theory, such as mentioned previously, the multivariate distribution. One example where it is applicable in number theory. Let me share my screen from. Let me share my notes once. In the PPT, we first initially discussed what the quadratic form was. It is essentially x transpose ax, or is equivalent to sigma of I is equal to 1 to n, j is equal to 1 to n, aij, xi, xj, right? And it represents a mapping from the real number space, from the vector space Rn to the real number line R. Similarly, we define the quadratic bilinear form associated with this as f of x plus y minus f of x minus f of y divided by 2. This is similar to how we can define A transpose B in the case of an inner product space as A plus B transpose A plus B minus A transpose A minus B transpose B whole upon 2. So as we can see, we can where phi is a mapping from Rn cross Rn to R. Essentially, from here we see that the notion of phi and f as associated with the matrix A, which also is known as the quadratic form matrix, is similar to the notion of the inner product operator defined for inner product spaces as A dot B is equivalent to A transpose B. However, here we can see that the inner product space is a satisfies all the properties of the quadratic space, where we take A is equal to I n cross n as our choice of the quadratic form. Further in the PPT we mentioned certain applications of the quadratic form, and such as in the multivariate Gaussian distribution, x is proportional to mu comma sigma, and here we write f of x is equal to 1 by root 2 pi kth root of 2 pi root 2 pi raised to the power k mod of sigma, who is the root of that, into e raised to the x minus mu transpose sigma x minus mu. As we can see, this represents something much like a quadratic form, and here we need that our matrix sigma is either positive definite or positive semi-definite. And when we get a matrix which is only positive definite but not positive, which is only positive semi-definite but not positive definite, we get a degeneracy, which basically means that the entire probability is concentrated around a single point. We also saw that it has applications in number theory. One of the most interesting examples in number theory is related to a theorem known as Lagrange's four-square theorem, which was generalized by Ramanujan, and recently it was also shown to characterize its universality. Effectively, Lagrange's four-square theorem is concerned with finding whether x squared plus y squared plus z squared plus states that we can find any integer I from just the combination of x squared plus y squared plus z squared plus w squared, where all of these are also positive integers, where x, y, z are also z and w are also positive integers. Ramanujan, one of the most brilliant minds of also studied this and further said that we can solve the general system ax squared plus by squared plus cz squared plus dw squared is equal to I to find certain possible combinations of A, B, C, D which satisfy this theorem. One of them was, of course, the trivial 1, 1, 1 as mentioned in Lagrange's 4 square theorem. Other certain pairs included 1, 1, 1, 2, and one more was 1, 2, 5, 6, so on and so forth. There were multiple such pairs. He particularly found 54 such solutions. In recently, there was a proof of a theorem which also stated that we can generate A, B, C, D only when we can generate 15 and 290, all the integers up to 15 and 290 in certain cases, and this characterized all possible solutions to A, B, C, D in terms of a trivial calculation up till the number 290. This was one of the number theory specific applications. It also finds application in geometry, as mentioned, for conic sections. We can characterize the surface of a conic section as x transpose ax plus b transpose x plus c, where this represents a quadratic form. Right. Effectively, we can also transform this into format of into some sort of sorry, never mind. We can also transform it into a quadratic, where this is a quadratic form, and analyze its property based on the definiteness of this, such as whether or not it will be a hyperboloid or hyperparaboloid or whatever. And it also has applications in other theories such as topology or advanced geometry and advanced linear algebra. So thank you. This was all for the theory of quadratic forms. Thank you.